Thank you very much to you and the other organizers for setting up this conference. It's very good to fill in the gap until next year in person. So I'll be talking about some ideas which are, basically in this paper, which is in the archive. The latest version is very recent. And let me go back straight to classical physics, where it was assumed that we could talk about trajectories of things. So you throw in a particle to some place and you can discuss that the particle went through some trajectory. Now, however, in the Copenhagen system of interpretations of quantum theory, this is not valid because you cannot talk about states that have not actually been measured. So you can only talk about what you observe in the end. However, we do have a strong intuition that, yes, there is a trajectory, but why is that? Now, the reason is that you can make different measurements. If I put this extra detector there, well, I will not detect a photon. Here, I will not detect a photon. Here, same thing, but here I will, and here, and here. So that means that there is a collection of measurements, which is like a space of measurements, where you find some geometric structure. So the straight line, which is the path of a photon, is not a path in the space of states of a particle, but rather a path in the state of measurement, in the space of measurements. Okay, so how do you formalize this idea? Well, measurements can be big things, so you don't want this. So let's go back again to classical physics for inspiration and see why it is that it works so nicely. In classical mechanics, systems have measurement-independent states. They are so measurement-independent that we assign reality to them. States are the real stuff. Then states are pretty abstract. They are defined by position, momentum, so intrinsic properties, which are basically sets of numbers. And these abstract states, they form nice spaces, like symplectic manifolds. You do geometric mechanics on them, etc. And this is also successful that it really reinforces the feeling that this is the right approach. So there are states, and these are real pieces of reality. Now, this whole thing crashed against quantum theory, as we know, hence the measurement problem. And there are zillions of ways to handle this. And well, one way is to go back to this idea that instead of taking spaces of states, let's consider spaces of measurements. So let's suppose that you handle quantum mechanics by saying that systems are defined by the measurements that can be performed on them, that the measurements themselves are defined by the observable properties which can be extracted from the measurements, where an observable property is just some finite piece of classical information, a sequence of zeros and ones. And then these abstract measurements will be things that can be investigated geometrically. They form spaces of some sort. So in this talk, the idea is to give an example of what such a space could be. So, well, it could be first a set of measurements, and then one could identify each observable property with a subset. It's the subset of all the measurements from which that particular property can be extracted. Let's see a little example. Suppose you have spin measurements of some silver atoms, and so the spin is quantized, so you have an upper deflection or a lower deflection by a fixed amount. And so let's suppose this represents actually three different measurements. There's Z plus, which means that you noted there was a hit in the upper section of the target. There's Z minus, which is, well, we threw in a particle and it collided with a target in the lower section. And there's Z, which says you just threw in a particle and anything could happen. So there are three measurements, and now there are two properties. U plus, which is the property that there was a hit in the upper section, and U minus, which means there was a hit in the lower section. And these are represented then as U plus as the set of Z plus and Z, which are the two measurements from which U plus can be extracted, and something analogous for U minus. This sounds sort of tautological. It's as if the properties and the measurements are almost like the same thing, but it's too simple an example in some sense, but let's stick to it. Now, when you have an intersection of properties like this one here, how do you verify this? Well, you can run the measurement a bunch of times until eventually in two different runs you extracted two different properties. So you know that both are possible for this measurement. However, you cannot do an infinitary conjunction because, well, you'd have, without other information, you'd need infinitely many runs, and this is usually not possible. But you can have an infinitary disjunction because a measurement belongs to an arbitrary union if it belongs to one of the sets in the union, which by definition is observable. So this means that we can take the properties to be the open sets of a topology. So this asymmetry between intersection and union expresses the finiteness of the observability of the properties. This is an idea which is borrowed from computer science in the 80s. Well, then, once you have a topological space, you can define the topological equivalence relation, and you can work in the T0 quotient space. In fact, we should make it a sober space, but I'm not going to get into details. So this is the topological layer on which everything would be built. So let me give you a flavor of what other kinds of constructions you could put on such a space. One thing, again, looking at that Z and Z plus and Z minus measurements, is that, well, Z is in fact like a disjunction of two measurements. When you run Z, you either do Z minus or Z plus. So if you have a property of Z plus, then that necessarily is also a property of Z, and same thing, any property of Z minus is a property of Z, which means that in this topological space, there's a specialization order, and Z is above Z plus and Z minus. Now, looking carefully at the operational way in which these disjunctions are measured really forces this to be the supremum, Z to be the supremum of the two others, and the supremum operation, which you postulate to exist for all pairs of measurements, needs to be continuous. So this is the first ingredient. Other ingredients are, well, the primitive notion of time, which says that you can compose measurements by doing one after the other. That will be a continuous associative operation. Another is a formal time reversal, which can be basically a mathematical construct that makes everything work nicely, even if in practice one might not know always what such a time reversal would be. And we can add a least element to the order, which is the impossible measurement. And this, plus three simple algebraic axioms, defines what I call a measurement space, which in fact has a lot more than it looks, because it's actually a complete lattice, because the topology interacts with the algebra and gives you that effect. Okay, the theorem is that if you take any C-star algebra and consider this collection max A of all the closed linear subspaces of A, and you put on it the so-called lower Vietoris topology, you get a measurement space. Mathematically, this is quite a strong gadget. It is a complete invariant for unital C-star algebras, which is a strong statement. From the point of view of measurements, well, C-star algebras are systems in algebraic quantum theory. So this is a way in which you find a measurement space that contains the measurements that you can perform on a system which is described by a certain C-star algebra. For instance, for the spin 1/2 measurement, the algebra is the 2x2 matrices, and Z plus and Z minus could just be the one-dimensional subspaces spanned by projection matrices onto the canonical basis, which is the basis of Z spinners. For X spin, you would do the same thing for the X spinners, and you get this fragment of the specialization order, in which X and Z, which are measurements of spin along X and Z, they're not actually the same measure. They don't coincide as they would in a Hilbert space representation, which is nice because they convey different information. Okay, so much for quantum measurements, but in real life we deal with classical measurements, things that look steady and unaffected by observers, and so let's see how we describe those. Starting with an example. Suppose one is looking at a wall, the wall of the lab, just by throwing photons at it. Now the photons, they don't have infinitely much energy, so you cannot actually get infinitely high resolution, so you don't see points of the wall. Well, there are no points in a physical wall, it's a very rugged thing, but anyway, the best you can get is to see a small portion of the wall. So let's represent this by saying that the measurements are the open sets of the wall, which is now an open rectangle in R2. So the measurement space will be the topology of W, this omega W, equipped with another topology, which is a topology of properties, which is a Scott topology, something used in computer science all the time also. So there are two levels of topology. The multiplication is just intersection of open sets, and disjunction is union. and the involution is trivial. So what is this saying? Well, we have a mental picture of the wall as a space with points, which is a mental image. We like that. We have reinforced that because we have geometry, which is based on topological spaces and manifolds, and you put geometry there. And it works so nicely that it sort of reinforces this idea that the surface is a collection of points. But what I'm saying here is that that's not how we see the surface. We see the data, which is the open sets, and that sort of translates into a model in which this data can be regarded to be open sets of another space, the space of, say, states, which is a derived thing. Why we feel this is natural, maybe this is up to psychology or neuroscience or evolutionary biology, but it's an interesting phenomenon. Okay, we can add more structure to the lab wall. We can have some symmetries. If W1 and W2 are 2 points, you can have an arrow from W1 to W2 conveying that a small region around W1 is copied, say, diffeomorphically to a small region around W2, for instance. And this gives you a groupoid. With a suitable topology, you get the space of arrows to be a groupoid over a space of objects, which is the lab wall. And now by taking the topology of the whole space of arrows of the groupoid, you get a new measurement space, where now the multiplication of open sets is the pointwise composition of arrows, and everything is again very natural. So these two examples of classical measurement spaces, one of them is static, just look at a wall. The other one has some dynamics, you can have some symmetries, but it's still very classical, and they're both topologies. And one can ask, so is this always the case? I mean, why would a topology arise as a model of the measurements in the classical setting? Well, there's a nice argument for that, which is, first, I can't really explain this very well here, but suppose that disjunctions are interference-free in a classical sense. Mathematically, I'll just require my lattice of measurements to be a distributive lattice, which is what you get for classical logic usually. Now, the second argument is interesting. It is a principle that classical means you can always increase your information because measurements don't contradict previously obtained classical information. So you can just keep on experimenting and you get more and more knowledge about your system. So this is like a classical computation process on a system which is not affected by our computations. And so this is like computation on a space of data. The data could be infinite, like function computing on real numbers. And it's a theorem that, again, comes from computer science, that when you compute on such infinite quantities, you have to proceed on the basis of finite approximations. And in order for that to work, the space of data has to be so-called countably based continuous lattice. Doesn't matter what this is. What matters is that when you put together distributivity and countably based continuous lattices, another well-known fact, you get something called a locally compact locale, which means that your space is actually isomorphic to the topology of a second countable locally compact space. So from a logical principle and an information processing principle, you get this fact that your set of measurements has to look like it's the topology of a space, even though the space is not really there. It's like you could think of it as an illusion, a set of points, which can be arrows of a groupoid or just points of a wall, which is generated by the mathematical theory of measurements. Well, then to make sense of reality, one needs to combine the classical things with the quantum things. For instance, here, I could combine a spin measurement with another one, but I want to turn the other one upside down. Now, turning something upside down is something you do in a classical measurement space of a groupoid. So this would be a composition of the z plus, followed by flip, followed by z. So in order to do this, you need to define an embedding of the classical space into the quantum one. And this kind of embedding is part of the structure which one can call a classical observer in max A. The interesting thing is that observers are not primitive notions at all. They are derived. They are structures. You don't need an observer to have an observation. It's like a measurement is something which is fundamental. It's there. The properties are there. And the observers are what happens when you organize measurements in sophisticated ways.
Just a quick note. So you have 2 minutes left. Are you wrapping up
That's what I
anyway?
need.
Good.
Thanks. Yes. I'll wrap up and then put another slide. So the point of view in this talk is that the measurement problem is created by regarding states as being real, like wave functions. then you have to explain why they change. So the problem can be formulated as, how is classical information extracted from each run of an experiment? You transform something into bits and bytes. So the alternative that I'm suggesting is that, well, you can assign reality to the measurements themselves, so that the production of a finite amount of classical information is like a fundamental manifestation of how reality appears. And this is, I think, I'm not misrepresenting Wheeler, saying that this is a sort of mathematical model of it from bit. It's it's saying that reality emerges from these appearances of classical information. So what does this have to do with consciousness? Well, this appearance of, well, measurements in classical information, it sort of forces one to think that this has to do with how we observe things. Now, there's a nice parallel that if you go back to the definition of qualia as originally formulated by Lewis in 1929, he would call this, well, qualia would be sort of the qualitative characters of things, of experiences, which could be repeated. I think this is more or less how we think of them. But he didn't consider them in isolation. He said, well, we also need a notion of pure concept, which is a meaning which is common to various minds that understand each other and that can communicate with each other. So the pure concepts are the stuff which can be, say, for instance, stored in synapses, which are used to communicate. So here the idea is that, well, when there's a measurement somehow, well, qualia they look like examples of measurements. Something happened that produced, it's a seed of classical information. But any finite portion of classical information associated to a measurement is what one calls a pure concept. So by arguing in the same way as I did with measurements, and I did this in 2019 in another talk, well, you can actually think of a space of qualia with concepts as open sets and, well, basically put it in the structure that I will describe for measurement spaces and say that spaces of qualia are measurement spaces. And then, well, for instance, selves, which are very complicated constructions that emerge from lots of different qualia that, well, occur in our perception and about ourselves. Well, there are examples of these big theories that you embed into a big space of measurements, and so they would be examples of observers. So the paper I mentioned at the beginning doesn't contain the word qualia in it. It's all about measurements. I mean, this thing is something that I've been elaborating on for some time, but it's not written yet. Anyway, so this was it. Thank you very much.